All right. Thank you very much for inviting me. So for this opportunity to discuss our recent work with Gleb Katausov. So I'm going to talk about some model of quantum field theory, two-dimensional quantum field theory. So let me start saying a few basic words about the integral of motion, local integral of motions in two-dimensional integrable quantum field theory. So suppose we have a quantum field theory in 1+1 dimensions, which possess an infinite number of continuity equations with the tensor density T mu 1 and so on. T is tensor density, so we choose the like on coordinate and rewrite these equations for each reducible for each component which transform irreducibly with respect to the Lorentz group in 1+1 dimensions. So the equations looks like this one. Then assuming then all density are periodic in the space directions, we can build the conserved charges. And integrability assumes that these conserved charges are mutually commute. Okay, this is a very basic stuff, and but we actually interested in situations, conformal field theory. So the situation when the theory doesn't possess any length scale. So in other words, if originally the theory was has a correlation length, the correlation length is assumed to be infinite, and then the equations, the continuity equations in this case became the conditions that the tensor density are chiral. So they depend only on one of the like coordinates. And in the terms, the local integral of motions in the theory becomes the operators. Again, they of course mutually commute, but the operator acts in chiral space of the conformal field theory, and the latest, as usual, can be decomposed in the irreducible representations of conformal algebra, extended conformal algebra. So in other words, the problem of simultaneous degeneralizations of local integral of motions became the well-defined problem in the context of the representation theory of infinite dimensional algebra. And you can think about this without any reference to the quantum field theory if you prefer to do so. All right, and now there are many different systems, there are many different sets of local integral of motions known. They're usually associated with the integrable hierarchy, like a KdV hierarchy, or equivalently KdV sine Gaudin hierarchy, the same one. Another one is a KNS hierarchy. The famous representative from this hierarchy are nonlinear Schrödinger equation or complex sine Gaudin equations. But today I will talk about some special set of local integral of motions, which is described by these formulas. But and this set related to the Gaudin model, Gaudin Hamiltonian. So let me explain. Gaudin Hamiltonian is not quantum field theory, it's just a quantum mechanical problem. But let me explain how, what is this first, remind you what is the Gaudin model. Gaudin model, it's a model which describes the, which is formulated in terms of the quantum spins. We have R quantum spins. So in other words, we have R representations of, we consider the R representations of the SU2 algebra, right? It's a spin algebra, usual quantum mechanical algebra. We focus on the case when the spins lives in finite dimensional representations. So GA here is integer of half integers. So it's finite dimensional representations. And then it was observed by Gaudin in the mid-70s that this set of operators, HA, they construct in this way, are mutually commute. And these operators, the interesting features of such a Hamiltonians, I call it Hamiltonians, is that depends on an arbitrary set of parameters Za. Right, so for any value of the parameters Za, there's Hamiltonian commute. They are not linear independent. Actually, there's sum equal to 0. You can easily check it. Well, and they also easily check the commutativity. It's just a few line exercise. All right, and the model is integrable in the sense that there exists a set of algebraic equations, the Bethe-Ansatz equations so called, right? And so it looks like this, right? The variables here is x and plus. I use the additional subscript here plus, but we'll see why. I will comment this later. Anyway, so we have a set of algebraic equations. If you solve them, then the spectrum of Hamiltonian given by expressed in terms of these solutions of the particular solutions of the Bethe-Ansatz equations. All right, the GA and ZT are fixed and given to us, right? The variables here, it's x and plus. Okay, and the model is rather simple. It's a very simple model. But it admits the natural generalizations, and in particular, that can be formulated for any simple Lie algebra, not for SL2. But in the beginning of 90s, it was realized that probably the model admits the generalizations, more interesting generalization, namely the Lie algebra can be replaced by the affine algebra G hat. So in this, as I explained, so in principle, that would be already, that would be the model of quantum field theory, conformal field theory, in fact. And as I explained, in this setup, the integrability would means that exists a set of local integral of motions. So they're given by the integrals of the local densities. And Ts plus 1 is a local field, chiral field. S plus 1 means the spin of this field, of the density. And so one may expect that there is a commuting set of infinite set of operators, usually commuted. What's important, they depend on arbitrary set of parameters. So it's a kind of the corresponding hierarchy contains a number of parameters. It makes the problem interesting. All right, and the important step in the development and in construction of such a formulation of this model was done by Feigen and Frankel, and well, slightly different notation, but in principle can be formulated in terms of Kac-Moody currents. The commutation relation is usually conveniently encoded by the operator singular part of operator product expansions. So this is operator product expansion for the currents, equivalent commutation relations. Then suppose, so once we have a Kac-Moody, so we have R copy of these algebras. Once we have for each copy, we can associate the Virasoro field. The construction follows this well-known procedure, Sugawara procedure, and so then the Hamiltonians are local integral of motions. So, and the corresponding densities in this case, right, the local densities has spin 2. Because the current, of course, has spin 1, Lorentz spin 1. So the densities for the Hamiltonian quadratic with respect to the current. So the operator looks like this. You see, they depend on Zeta. It looks similar, somewhat similar that usual Gaudin model, but this is a fine variant. And it's simple exercise to check that the operator, this operator, mutually commute. This is it. Again, few line exercise. Maybe a little bit. Okay, but that was conjectured by Feigen and Frankel. There exists the Hamiltonian. These are Hamiltonians. Only the part of the infinite commuting family of operator, infinite set of local integral of motions, right? And so in certain sense, the model is integrable. And immediate questions how to write the Bethe-Ansatz equations. Remember, for the Bethe-Ansatz equations for the Gaudin Hamiltonian, it's easy to write. Actually, can be obtained from the certain limit of the Bethe-Ansatz equation for XXX spin chain. and homogeneous XXX spin chain. But in this situation, for the affine algebra, it's not clear how to, there is no such a procedure. And the Fagan and Frankel, actually, the idea of Fagan and Frankel was use some property of the original, generalize some property of the original Gaudin model to write down the Bethe-Ansatz equation, even you don't know how to construct. So it's basically the way to how to guess the equation without derivations. And the idea actually about how the Bethe-Ansatz equations you can find in the evergreen books of Whitaker Watson, in particular in the chapter which is discussed the separation of variables for the Laplace operators in the ellipsoidal coordinate. So you can find the equations, which is this one, and this equation exactly what we have for the Gaudin model. The only difference between these two set of equations that here the small r is equal to 3. And the reason is very simple, because Whitaker Watson worked in three-dimensional space. If you consider the ellipsoidal coordinate in r-dimensional space, there is a simple generalization, then they indeed get the set of Bethe-Ansatz equations for the Gaudin model this way. And so I will not follow any not discuss how all this handled in the Whitaker Watson. Let me explain in my own words what's going on here. So once you consider you start with the Laplace equation, try to separate the variables, then you get the second-order differential equations. And similar, for example, for spherical coordinate, you get the Legendre equations. In the situations with the ellipsoidal coordinate, you get the equation like this, and it looks like a Fuchsian equation. So the equations with the regular singular points. In fact, together with the singularity at ZA, it also has a singularity at infinity, and the conditions that the infinity is regular singular point is that the sum of the residue is equal to 0. And but equation, so in this case, suppose it's true, then the Fuchsian equation, but the equations which is appeared in this context is very special one, namely this equation, all the singularity, not just the regular singularity, they're actually apparent. What does it mean? A singularity ZA is called apparent if the ratio of any two solutions of the differential equation is single valued in the vicinity of that point. So in other words, if you have a singularity, then a regular singularity, that of course at this point, at singularity, you have a branch point usually, typically. But here, the singularity is so special that it's not it's a single value. To be more precise, you should state it for the ratio. And the remarkable phenomenon happened when EA, the residue, is potential coincide with the set of energy of the Gaudin Hamiltonians. Then in this case, all the singularity are apparent. So in this situation, the solution can be has a very simple form, right? You see that as and the meaning of the set xm plus, which is the solutions of Bethe-Ansatz equations. Solutions of the Bethe-Ansatz equations. It's a zeros of the wave functions. You see the solution has a branch point. In general, when GA is half integer, that it has a branch point, but it's square root singularity. When you consider the ratio, it always becomes a pole singularity. I write only one solution. There is another solution, psi minus, and it also has a zeros, very similar formula, and you can write the Bethe-Ansatz equation for the zeros of another solutions, and it's just alternative descriptions of the same systems. So this is the reason why I use subscript plus. Anyway, so here we probably we have a link between the spectrum of the Gaudin Hamiltonian and the class of differential equations possess certain monodromy property. And this is rather general phenomenon. Now it's usually referred to the ODE-IM correspondence. But you see, in the situation like this, IM means integrable mode. In situation like this, when integrable model is a Gaudin model, there are not much use of this correspondence, because you can construct the Bethe-Ansatz equation, you can diagonalize, you can do everything without any reference to differential equations. You know how. And the site with the ODE is also rather simple, and you can investigate the problem without any references to the Gaudin model. So this link is just a curious relations and nothing special. But the situation becomes much interesting when the link exists between the differential equation and integrable quantum field theories. And then the ODE still can be investigated by the standard method just of analysis and the classical analysis. From other side, the integrable quantum field theory, sometimes it's difficult to do. And in a situation like a affine Gaudin model, you don't know how to derive a Bethe-Ansatz. So the idea is to find the differential equations, find the conditions which guarantee the certain property of monodromic property of the equations, and that gives you the Bethe-Ansatz equations. Of course, it's a tricky way. It's not a honor way to handle the problem, but then you can check, you can do some consistency check and see that everything worked well. Okay, and this was actually the idea of the Fegin and Frenkel, and they said that we have these Hamiltonians, and somehow the idea is they propose the differential equations corresponding to this Hamiltonian, and then it allows one to write the Bethe-Ansatz equation. But their work, they didn't explain how to extract the spectrum. They give the Bethe-Ansatz equation, but they didn't know how to extract the energy from this equation. It's a kind of curious situations when you write the equation, but what to do with them still don't know. But anyway, so in our recent work with Gleb, we propose another model, which Hamiltonian now looks like this. And again, everything, the notation are the same. We use the current R copy of the Kac-Moody algebra. We use the Virasoro fields here. And so everything, this looks similar to the usual affine Gaudin model, but it's important that the model contains the parameter beta. And when beta goes to 1, right? Oh, sorry. When beta goes to 1, then this term is disappeared. This term became infinite. And if you assume that somehow the parameter zeta goes to infinity, you can rescale the variables, and finally, after certain limiting procedure, get the affine Hamiltonian. So this Hamiltonian actually deformations of the affine Gaudin Hamiltonian. And we propose the differential equations for ODE IQFT correspondent for this model for all states, and also fully describe the spectrum in terms of solutions of corresponding Bethe-Ansatz type equations. So how the differential equation looks like in this case, this is this still differential equation with second order. The potential in differential equation contains two terms. The first one, it's very similar that we have an ordinary Gaudin model, but the number of singularities now it's well, it's more the number of singularities now not only in the points zeta, but also some auxiliary points W alpha. But anyway, these terms are very similar that we have for ordinary Gaudin model. We also actually add some extra term, which is with this regular, which is singular point at z equal to 0, right? It's controlled by the parameter a. In principle, you can for certain value of the coefficients and from the singularity, you can actually make it 0. But it's as usual, it's very convenient to have such a term. Well, and so this is a kind of generalizations of usual Gaudin model, but there is an extra terms which is proportional to parameter kappa. like spectral parameters play the role of spectral parameters, and this the extra terms I would call it affine term depend on deformation parameter beta, and the only place where we have the deformations beta it's through this parameter height. Anyway, so this is equations, and then we said that let's consider the equation of such a class and formulate the conditions that all singularity are apparent except 0 and infinity. And that it's immediately, well, there's some standard procedure how to write the local conditions for this, and this the result we get the system of algebraic equations which would be play the role of beta ansatz equations for the Gaudin model, generalized Gaudin model. Generalized because it's deformation, so usual Gaudin. Okay, so then suppose you solve it, then the energy spectrum can be obtained through the solution by some formulas. Well, I not give the explicit explanation, write the equations and write what the dA here means. I don't think it makes sense here. So if you're interested, you can find in our paper all the notations and all the exact relations. Well, in fact, yes, please.
So what is the loop parameter of the affine Lie algebra in this equation? The loop variable.
The loop variable kappa.
Kappa.
Kappa. It's a spectral parameter.
Okay, thank you.
So it's some power of lambda. Lambda is usually spectral parameter, but it's more convenient to use this kappa. Right. So kappa equals 0 would be a non-affine case. If you set kappa equals 0 and L equals 0, L numbered additional singularities here, then you get this just a Gaudin case. Okay, but I'm not going to talk about the differential equation anymore. Instead, I'm trying to explain how this how the local integral of motions, how the Hamiltonian can be constructed, what the procedure. And the procedure. And the procedure actually, well, the older construction follows the old, very old idea, which is formulated in our work with Bazhanov and Zamolodchikov long time ago, and follows just basically it's some formalizations of the ideas, Baxter idea, Baxter integrability, how it works. So the starting point, the algebraic setup here was understood by Drinfeld and Jimbaum when they introduced the so-called the algebra, which is universal enveloping algebra of affine Lie algebras. So G in my notation, G is Lie algebra, G hat is affine variant, UQ. J hat, it's universal enveloping algebra. It's usual notations, and I will talk only on the simplest case of SL2 algebra. So idea, the central ingredient in the construction is universal in matrix. So if we, and this is object which belongs to the tensor product of two universal enveloping, quantum universal enveloping algebras. And the idea is take the universal R matrix and specialize the certain representation so along the first tensor component. So representation can be constructed in this way. So first you take the evaluation homomorphism, so homomorphism of this quantum algebra to the loop algebra build on the non-affine algebra QJ, and whose element whose elements are formal Laurent series in terms of the spectral parameter lambda. You will also specify the representations of a QJ, and after this, the object which I denote by L, it would be the matrix finite dimensional matrix. The size of the matrix depends on the chosen representations, 2L plus 1, 2L plus 1 matrix. And the master equations, the formal algebraic relations after these specializations became the Yang-Baxter relations. So basically, that is how to generate the certain solutions of these Yang-Baxter relations. Okay, and so in the situation, and this is the simplest Lie algebra SL2. The R matrix is well known due to the work of Haroshkin-Stalton. Explicit formula is rather simple, and you can do it explicitly. As a result, what you get the series in terms of the spectral parameter lambda, and the coefficient in this series, that would be the matrix. E plus, E minus are matrices, right, and depend on representation, but also the coefficient would depend on the generator x0, x1, which is generator of Borel subalgebra of the OQSL2 hat algebra. So everything you see here, everything would depend on the Borel generator of the generator x0, x1, and also Cartan elements, H0, H1. So this is the structure of this matrix. Just illustration. I give this form of illustration, and then you can take the trace over the representations over the matrix representations. So in our case, matrix representation, the space is 2L plus 1 dimensional space. You take the trace and you end up with the formal series. I denote this trace by T, and using the terminology of statistical mechanics models, integrable models, this object called transfer matrix. And this transfer matrix would commute for arbitrary values of lambda and lambda prime, and the commutativity guaranteed by the set relations. What's important, the only set relations are important in the construction.
Give another one, because otherwise people at home, they can't do it. Yeah. Just 1 second.
Stop. Okay, and they built and they involved only the generator x0, x the generator of Borel subalgebra. Of course, the most interesting questions is the choice of representation. If you choose it, then you specify the physical space where all this garbage acts, right? And there are many different representations for Borel subalgebra, but the interesting one, which more interesting situations appeared. Generator of Borel subalgebra possess the form of integrals over the certain vertex operators, plus and V minus. So it has schematically it has a structure like this. And the conditions, which is important, that the vertex operators are not local fields. They satisfy the certain Brady which looks like this, right? It's allowed one to interchange the order of the vertices. They also require they satisfy the certain quasi-periodical boundary, quasi-periodical conditions. It's non-local quasi-periodic fields with vertices. All right, and if suppose you find such representations, then there's some interesting phenomena happened. Then this huge this is long series in lambda combined with very nice expressions, namely it became the path ordered exponent. So what I said that using the Braden relation, you can reorder the integral in such a way that making path ordered one. And the result, you have an expression like this, and you can easily recognize the operators, which looks like evolution operators for in interaction pictures for some quantum mechanical, for some quantum systems. So you see that in this model, the corresponding model would involve some quantum field theory degrees of freedom, which is encoded by vertex operator V plus and V minus, which is coupled with the spin operators, sigma plus and sigma minus, finite dimensional spin. You can choose it whatever you want. And this is this operator, this evolution operators for the model, which in condensed matter usually refer to the quantum model or quantum type model. So that describe the interactions, the bulk degrees of freedom with the impurity spins. And for this reason, all this can be, all I'm talking today can be translated in the language of the condensed matter in the context of these impurity problems, but I will not go in these directions. Okay. Now the question is what type of vertex operator we can choose, and there is many different ways to do so. And original in our original work, our original work will focus on some particular problem, namely quantizations of the Korteweg-de-Vries equations. In that case, the vertices looks very simple. It's just the exponent of the exponential Carrel-Bose fields. But this is for KdV. If you, for example, take the nonlinear Schrödinger equation, then the representations, which also in the class of SL2 integrability, where the vertices expressed now in terms of two Bose fields phi and theta, and this is how they look like. So it's another way. This representation gives to another integrable hierarchy. But the most relevant for us will be the representation of Borel subalgebra, which I introduced, a long time ago, actually, and it's based on the Kac-Moody currents. And to be more precise, they involve the ZK parafermionic fields. The Kac-Moody current is known from the work of Fatiev-Zamolodchikov. The Kac-Moody current can be expressed, can be realized in terms of the parafermion field psi plus minus here and the single Bose field phi. And so the vertices V plus minus, which is paired in the construction of Borel of the generator of Borel subalgebras, now looks like this, and you can easily see that it's just deformation of the Kac-Moody current, and parameter deformation is beta. When beta is equal to 1, then V plus minus exactly equal to G plus minus. But if beta less than 1, then the V plus minus will be just deformation. Parafermion remain the same, of course. And under such a deformation, the parameter of quantum group Q, it's related to the beta. So beta equal to 1 correspond Q equal to -1. So it's kind of classical situation. So the parameter is 3, they're non-deformed. All right. So that is in this situation we have this is some representation, some realizations of Borel subalgebras, and now so you see that there are many different realizations of Borel subalgebra, and they correspond to different integrable hierarchy, integrable commuting set of operators. And the questions, immediate questions, how to construct the local integral of motions. You can construct the transfer matrix, but the transfer matrix, it looks, well, at least the coefficients in the Taylor expansions, not a local operator. So how to construct the local operator? Remarkably that there is a simple algebraic procedure to do so, to construct the local operators. And let me explain it using this example with the parafermions. So the idea is the following. So the first step in the construction of the local integral of motion, it's a construction of certain W algebra. It goes the following. So first we consider all possible local field with a given integer spin S. I do not buy this. So in the case under considerations, so this is all field which you can be built from the field phi and parafermions. Of course, the space LS, right? It's a finite dimensional space. You can, in quantum field theory, with the given spins, you cannot build too many fields. It's a linear space. You can add two densities at the same spin, and it would still spin the local. Still, the sum would be local field, and also it's finite dimensional space. Then, among such a field with the given spin, Lorentz spin, you search for the. You choose first of all. You choose the certain vertex V plus. You can choose V minus. Doesn't matter. So let's choose the V plus, which occurs in the constructions of the barrel V generators, and search for the local field given spin, whose operator product expansion with the vertices total derivative. It's a derivative, total derivative. Schematically, it looks like this. Using the physical slang, such a field is called. This condition just people say that the field XS commute with the screening charge, and the screening charge in this case it's just a generator of one of the generator of Borel subalgebra. So this formal integrals over the vertex V plus. Okay, so and not any local field satisfied. So it's the local fields which commute with the screening charge. It's some subset of linear subset or subspace in the space LS. And what's interesting that all the local field commuting with the screening charge form the closed operator algebra with respect to operator product expansions. So if you take two fields, if you have one field which commutes the screening charge, another one to also commute, and then the operator product expansion, you generate only the fields which is commute with the screening charge. It's very easy to check. And in other words, and such an algebra is known since the seminal work of Sasha Zamolodchikov is known as the W algebras. And so with the given set of, if you specify the set V plus, the screening charge, then you can construct the certain W algebra. Okay, but this is the first step in the construction. The next step so here's an example. Maybe to be more specific, let's consider the example. So the non-trivial field, the non-trivial local fields which commute with the screening charge appeared on the for spin equal to Lorentz spin equal to 2. So the space L2 spent on the square root of the second derivative of phi, the second derivative dphi squared, and the field W2, which is a spin 2 field which appeared in the operator product expansions of the fundamental parafermions, and it's nothing but the energy momentum tensor for parafermions. Okay, so this is a linear space, and then we can adjust the coefficients, consider the general linear combinations of the three fields, and adjust such a way that they commute with the screening charge, and the single field up to the overall multiplication of clash factor. And the field looks like this. And nothing interesting happened for the field spin 3, but for the spin 4 fields, there are three fields, which are derivative, second derivative of the fields x2, right? The squared of spin 2, the squared means that it appears in the first regular term in the operator product expansions of 2x2. And also some extra field x4, which is built out some explicit form. We can write the explicit formula, which involve the fields W4, the next term in the operator product expansions in the parafermions. Anyway, it's difficult to work with the parafermions. Instead, you can bosonize the parafermions and express everything in terms of the bosonic fields, bosonized in terms of the field alpha and gamma, alpha and gamma, then all the field from the double algebra would be differential polynomial in terms of the three Bose field, phi, alpha, and gamma. And we have using this Bosinization formula give you some bonus, because you see parafermions original initially we start with the Kac-Moody algebra with the integer levels, but if you take a look on this formula for Bosinization of parafermions, in principle you can treat k as arbitrary numbers, and this allows one to introduce a double algebra for arbitrary values of k. Actually, this double algebra it's known for a while and was studied in the work of Fedin and Semikhatov. They associated this algebra associated with some exceptional super Lie algebra 2-1. Yet I don't know how to pronounce it. Well, anyway, so that is but also this algebra studied in the context of some boundary flows with our works with Sasha Zamolodchikov. We call it simply it's corner brain double algebra. I call it. But anyway, so this corner brain double algebra it can be defined for depend on parameter k depend on beta parameter deformations, and also k can be which is arbitrary. Okay, and this is the first step in the construction of local integral of motion. The next one is involve the vertex v minus, which is not yet appeared in our discussions. So we search for the local field given spin commuting the screen charge, but such that the operator product expansion of such a field with the vertex v minus possess the following structure of operator product expansions. And this is very general formula, of course, nothing said, but we require the residue R minus one. It's a total derivative. And then it is a standard way to argue that if you build such a field, if you can construct certain linear combinations of the field of the double algebras satisfying these conditions, then the integrals over such a field would be local integral of motion. They mutually commute, also commute with the transfer matrix. And that gives you effective way to construct. So this way you see, if you specify the vertex operators, then in principle you can pure algebraic way to construct the set of local integral of motions. In particular, in the case of with this paraferm simple case I just mentioned, discussing here as an illustrations, there exists this set of local integral of motion was introduced by Kiev. And it is this set, and in the case when the k is negative, they are local integral of motions for the hierarchy of integrable hierarchy of a certain nonlinear sigma model, which is known as a three-dimensional sausage or Fatiev model. So that is a way. So that is a. It's also this set of integral of motions created with a certain integrable hierarchy. Okay, so then principle, the idea of the construction is just to find another new generalization, so it's a new representation of a QB minus, and so instead of one parafermions, parafermions and Bose fields, we consider the R-independent copy, and then we should take the certain unlocal field, which is deformation. Again, it's a deformations of the Kac-Moody current with the parameter beta, parameter of deformations. And then the statement, then the following is taking the sum over this unlocal field, V plus and the V minus, you get the integrating over, making the integral over from 0 to pi, you get the generators of the Borel subalgebra. And you see, I write here the constant. You can construct make this construction for arbitrary of choice of the parameters ZA. In principle, you can put the same. You can ask me, why don't you put the parameter extra parameters in front of V plus also? But the point is that after the trivial shift of the fields, Bose field, you can always adjust the coefficient such a way that he is one, then the number of independent parameters only R. My point, because otherwise, so in principle, you can write 2R parameter by shift of the field. It will not make any changes to the theory. So the number of independent parameters are. Okay, and so we specify these vertex operators, and then after doing, it's difficult in these situations, technically to construct the double algebra explicitly and construct the local integral of motion. It's much more in work and work. But after we come to the conclusion that the fields which commute with the screening charge which satisfy these conditions form the non-trivial double algebra, and this double algebra would depend on number of parameters. It depends on the parameter k. R, it's a number, integers, and parameter k. And again, you can think about the k as arbitrary number, not necessarily integers even, because for the same reason as for the case r equal to 1. And also they depend on central charge. It's another way to introduce the parameter, because beta, you can parameterize the central charge. Capital K, it's a sum over the Ka, so it's not independent variable. So this is a conjecture which is checked for different situations. It's no proof of this, but it looks like. And the next step, finally, to construct a local integral of motion, we need to find the densities, local densities, which is satisfy these conditions. And again, doing the explicit calculation, you find that we come to the conclusion there exists an infinite set of local integral of motion associated with this choice, with these representations of the Baryk subalgebra. And explicitly, again, it's difficult to construct for the local integral of motion with the highest spin densities. It's difficult, but fortunately for the case of the Hamiltonians, by Hamiltonians, I mean the local integral of motions whose local densities has spin, Lorentz spin 2. And explicitly, you can construct such a mutually commuting operator, and they express in terms of the Bose field and the parafermions, as you see. And finally, everything can be, we can return to the currents and parafermion. All this can, the same, this formula is just a different way to write this formula. Fortunately, we can now return to the currents instead of parafermions, use the currents, and as a result, you get the Hamiltonian, which I call the Hamiltonian for generalized affine model. Okay, so what's the lesson we learned from this? So we have this Hamiltonian, by the way, it's easy to check that, not easy actually, but it's possible to check that the Hamiltonian are mutually commute. So the important property of the model, which we introduce here, it's the fits within the framework of standard Yang-Baxter integrability, and so the Hamiltonian, a part of commuting family of operators such as transfer matrix. It's also Q operators. The Q operators just a particular for a particular type of transfer matrix as well. So, but everything which we know from the integrability, from the Baxter integrability, can be applied to such models. And this is kind of surprising because the people believed for a long time that the affine Gaudin model, it's not in a class of integrability. You need to introduce some extra structures, but this is not true, actually. Anyway, so we in the work, we also introduced the ODA IQFT correspondence and described the spectrum of the Hamiltonian, or this Hamiltonian. Okay, as for application, probably I'm out of time already, but maybe I mentioned. So you can ask me what's the integrable hierarchy corresponding to this model, and this question is still open with some preliminary result, but it looks like that the model, correspond the hierarchy of the integrable nonlinear sigma model recently introduced by Del Duc, Lacrosse, Magro, Viseda. It's built out from the collections of the Vesuzumina models. Also, I already mentioned the model. It's a multi-parametric generalization quantum model, and recently that's a long story, long history of all of this, but recently it was appeared in the recent work. The interest was renewed in young generations of physicists. They rediscovered many features of the model. So it's a very interesting. I think it's some interesting applications for the condensed matter here. And as also I would say that this generalized Gaudin model has described the scaling behavior of certain lattice systems. And this is a lattice system, one of the oldest one, actually. It's original Baxter, in the simple setup, it's original homogeneous six versus model, which is introduced by Baxter in the 70s and the 71. So actually it's a starting point for the integrability, but people might, for some reason, not study this model in details. But anyway, so this Gaudin model, generalized Gaudin model, described the scaling limit under certain values of parameter. The model is critical. Its scaling behavior described by this model. And in particular, the six vertex and homogeneous six vertex model involved the solution of trigonometric Yang-Baxter equation and the parameter of Q of this anisotropy parameter for their matrix. It's related to the beta in this way. So in the limit beta goes to 1, trigonometric R matrix became rational one. It's Yangian limit, and the model actually, as we already mentioned, is related to the affine limit of the Gaudin, affine Gaudin model. Okay, thank you very much for your attention.
Are there questions to Sergei?
There is one from home. There is one question from home.
Okay. Hello, Sergei. Can you hear? Can you hear what I say? Okay. So I think you briefly mentioned, but I have a question regarding this affine procedure. How generic this statement is in total? If I follow this affine formalism with a universal enveloping Q deformed group, and I follow this procedure once, for which class of models this procedure works? Like if I'm able to construct, if I assign the Virasoro field to each copy, then I can construct the vertex operator and follow your condition and construct, eventually integrate and get the local integrals of motion. So the question is, for which class of models do you think it works? For example, you mentioned the nonlinear sigma models. Can it, could it work, for example, for this 4-parametric sigma model that follows from your construction, which follows from the harmonic map problem? Hello?
I suspect that in 2 dimensions, I suspect that in 2 dimensions, the 1 + 1 dimension, like the only integrability type, which is really known, which is known, it's a Yang-Baxter integrability. Well, it's maybe not easy to find. You know, there are many models when the R matrix it's not clear how the R matrix and how it is. You see that there's some. Well, let me say a few historical. Some comments about the history of if you read the Fadeev Takhtajan book, you probably the central point of this book is the TTR relations, and all the construction of integrability based on the classical Yang-Baxter algebra. And it works well for the class of model like nonlinear Schrödinger equations, the Sine-Gordon equations, and even well. But there are many different at the time in the 80s and 70s. It was constructed many interesting models, like in particular the model from the class of linear sigma model, where it looks like the construction doesn't work because there is no classical Yang-Baxter relation. So the algebra, Poisson algebra, should be replaced by some other algebra, and it's not clear how to quantize such algebras. And so this is a famous problem with the non-neutral locality. And there is some opinion that this is the model is very different. It's a different class. But for me, actually, the old situation I studied, finally, I found the model, it meets the representations. There is no problem with the locality. And this is just a problem with the choice of the gauge. Of course, if you have if you choose the Yang-Baxter relation, the Yang-Baxter algebra depends on the gauge of the zero curvature representation. And if you choose you can consider any gauge, and the zero curvature representation will still work. But the algebra, you lose the structure of the Yang-Baxter algebra. And in my opinion, that all the integrability, the classical integrability, at least in non-relativistic quantum field theory, all in the class of Yang-Baxter integrability. So in principle, I believe that the scheme I'm discussing here. So when you start with certain universal matrix and they specify the certain representation, it should work for nonlinear sigma model, integrable nonlinear sigma model as well. So at least I don't know. Well, I don't know. I just think the all example well, you know, there is list of example. Maybe the first example of nonlinear which with this problem on locality, it's a so-called complex Sine-Gordon model. It's the simplest example. But now we know the gauge where it's local, where there is no this still in the class of Yang-Baxter integrability. So my answer to your question, I believe that there's nonlinear sigma model which is integrable. I think can be handled with this. With the framework of the Yang-Baxter integrability.
I see, thanks.
Yeah. Can you hear me? No.
Yes, please, Jean-Emile.
Yes. So I was wondering. So you introduced some new W algebra. Can you obtain them using this Drinfeld-Sokolov reduction?
Can you repeat, please, Jean-Emile?
Can you obtain this? Yes. So you introduced this new W algebra. Can you obtain them with this Drinfeld-Sokolov reduction? Oh.
I cannot. Could you translate it?
Sorry, maybe I will just write down.
Drinfeld circle. No, I don't think that it's
No?
another class. The Drinfeld circle of reduction. You see, there are many different. I cannot say for sure because I never did it. But there are many different double algebra which is not cannot be obtained through the Drinfeld circle of reduction, at least in the orthodox formulations. The simplest example I would because Drinfeld circle of reduction makes some assumptions about the Lax operators. And the simplest example I know, which is not in Drinfeld circle of class, is Getmanov 2 model, complex sign Gaudin 2 model, number 2. There is two complex sign Gaudin, complex sign Gaudin 1 and complex sign Gaudin 2. And the model which is not the double algebra for this model cannot be obtained through the Drinfeld circle of reduction. I'm not sure about this one. I never thought, but maybe. But you see the huge the number of parameters in this algebra. In principle, now you can consider the different algebra. You can SL2 is just example. Of course, you can repeat it for the higher rank algebras and with the arbitrary values of the parameters of the levels. And I don't know. I know nothing about this. Maybe there's some examples of this double algebra already studied. And so I don't have much experience about the property, not studied as well. And even construction of the field, and even this is just a set of conjecture which is obtained by the very hard works, and I cannot do such a work without my collaborators, young collaborator. I should advertise it with he is great. But for mathematical, so the mathematical structure of this algebra is still unexplored. Yeah, that would be very interesting to understand. I think because the scheme looks rather general, I would say. So.
Okay, I see. Thank you.
This is what you asked, Jean-Emile. You asked this, yes?
Yeah, indeed. Thank you.
Because I interpreted, I wasn't sure because nobody was able to understand what you asked. I guessed, knowing your interest.
I don't have.
So, but I have another question. Can you say some words about the ODE side? So about the potential.
What you see, I can okay, good. Now it doesn't work. Okay, let's turn to the differential equations. These equations in the
also how did you derive it?
Okay, let me make some comments about the historical. First of all, this is these terms, right? Let's take a look on these terms which depend on L. Capital L here, it's a level of the double algebra, a representation of double algebra.
So these are also excited states.
So let's first of all set L equals 0.
Yeah.
That it was just a primary double field. So we're out of this, right? And then this is a primary field, and if in the simplest variant for the vacuum, GA is equal 0, and in principle you can set this term also 0, right? Actually, you can for the certain state, for the certain given state, you get you can set T equals 0. This is for ground state, if you want. For the ground state, you can neglect this one. Then what you have here, if, for example, you can adjust parameter here, so there is no the first term. And what you have here, it's a polynomial. So the differential equation is just it's a Schrödinger equation with a general polynomial potential. And this problem was studied by Voros. The functional relations and the quantizations, the exact Bor-Zimmerfeld condition was studied on this problem. So this is just particular case of this problem. Then the people also studied the situation when all Ka is equal to 1. So all the roots of the polynomial are simple. Because in this situation, the structure of the Stokes line simplified and easy to handle. So a particular case of these equations well studied in literature, and also what's say. I think in your works also you in recent works in the sine-Gaudin model,
We do.
the polynomial functions.
We do, yeah.
I don't remember that you studied the excited state, but you
Not
discussed
yet.
the massive model, right? And the immediate one of the questions how to write the massive variant of that massive variant. I would say that it corresponds to the sigma model. Deformations of the sigma model.
That was my second
There
question.
is another
Yes.
question from the.
Yeah. But of course the nonlinear sigma model is massive one, and we're just talking about the chiral limit.
So I would like to make a comment or and ask a question about really this ODE, because like in the construction of Dorian, Tateo, and you with your collaborator, you get the solution of the beta-ansatz equation are the spectral determinant of an ODE. But here is a different setting. The beta-ansatz equation are the trivial monodromy condition for a given ODE. So,
Wait a minute.
so in the ODM correspondence, you have the solution of the beta-ansatz equation of a quantum field theory is the spectral determinant of an ODE. But this is something different.
Why? It's also spectral determinant.
But here the beta-ansatz equation are the condition for the apparent singularities.
This beta-ansatz equation just specify the potential. Suppose we choose the state, specify the potentials, then we have a spectral determinant, and the parameter, spectral parameter would be kappa, and it has zeros. And you see, I would say the scaling limit of the spectral functions, it's just a spectral. It's a scaling. It's a spectral. If you take the Baxter model, 6-vertex model, right, and consider the scaling limit, then you get the spectral determinant for these equations. And the zeros of the beta-ansatz, the zeros of spectral determinant, it's just the usual zeros of beta-ansatz for the 6-vertex model. So I don't see much difference between this. Everything almost
for me, it's totally different. Maybe I don't understand really.
Maybe we discuss this point if you want, but I would say that this generalized Gaudin model follows almost identically all we know from KDV. I don't from the KDV case. It's just technical generalizations that I try to explain that we just different representations of the Borel subalgebra and differential equations. But all we said about the KDV and spectral determinant that can be repeated for this. Actually, the functional relation remained the same almost. Yes. Z equals 0 also in the case of the KDV, we have a centripetal potential, which is convenient to introduce. And actually, it's to describe the full Hilbert space, you need to introduce it. It's a regular singularity, but this is also a regular singularity, right? This is a regular singularity, Z equals 0. Yeah, so the same. I don't see it, you know, the potential. This is like it's maybe written a little bit different form than in KDV with the monster potentials, but this is just this is the same. No, I don't think.
Please. There is a question online.
It's very difficult to understand. What's maybe my problem with the hearing.
Please, Anton, please speak slowly.
Yeah, okay. Sergei, maybe one more quick precision is it was mentioned briefly on your last slide, but this is along the lines what David Gaudin is doing. For example, when you mention this Kondo model, I'm just thinking there is very important implication in the context of holography when people, you know, having not just regular one impurity, but have two interacting impurity spins, which is doesn't matter, but people call it RKKY. And this is also important for holographic description, but people have zero understanding about the integrable part. I'm just wondering, could it be thought the other way around, that can we understand, say, this two impurity spin problem in terms of your generalized affine Gaudin?
I cannot say anything about about the holography and relation to an equal to supersymmetric higher dimensions. So this is some, well, I don't know. You see, all the what I'm not an expert and I don't understand much about the, let's say, the versus Chern-Simons in 3 dimensions, in 4 dimensions, right? That all this business come out. But you see, it looks nice, but I don't see much use of all this business for the integrability itself. They're just reformulation. For me, you see, that is kind of just a tautological reformulations of the problem. Because you start, we know that the central point on integrability is zero curvature representations. And of course, so the flatness conditions. And yeah, the Chern-Simons is give the flatness equation of motions, and you just formulate it some way, you know, which involve the string theory, but in the context of the solutions of the problem, I don't see much use of all this. Well, and to understand, you see, when you said me that this should be understood in the context of the higher dimensional gauge theories, I should understand what is, does it help me to solve the problem or just a tautology?
No. Again, that's what I'm asking.
Unfortunately, the string theory looks like mostly just tautological reformulations of the well-known facts, and then again and making the new string revolutions at each point.
No, absolutely. I'm not asking about reformulation. I was wondering if one can understand if, because the present, like what people do in CMT, this is purely, forget about holography. This is purely a CMT problem. For example, can this two impurity spin problem be reformulated, say, in this affine Gaudin, generalized affine Gaudin formalism? Maybe there is more understanding on integrable structure of such model. The holography is a second question, because people don't understand the integrable structure at all, even on the
structure of what?
of this, if you want, generalized Kondo model.
Kondo model. Okay. So the Kondo model, right? This looks like a way to construct the set of integrable models, integrable generalization of Kondo model, which is multiparametric. It contains the many parameters. But as usual, in the situation, real condensed matter situation, if you have a complicated system with many parameters, they are not typically integrable. And the parameter you use, the real condensed matter people are very skeptical about such things, because you find something which is integrable, but we are now in multiparametric, the space of very huge, and we choose the certain integrable cases.
Sure.
I'm not sure that all this may be applicable for the real condensed matter situations. The success of the original Kondo model was that the number of parameters very small, and the Kondo model with the one impurity spin, with the spin 1/2 impurity spin, and this indeed, well, can be found in the realistic systems, but But in this setup, the space of interactions is very small, and the only interaction constant actually corresponds to the integrable situation. So if you ask me about the applicability for the condensed matter problem, I'm not sure that it's really very interesting for condensed matter people, but it's interesting for us because it's something one of them, it's some general, setup, which is integrable setup with many parameters. I don't know, well, you know, and how it's useful for real physics, I'm not.
No, I mean, to find the ones that are integrable with multiple parametric in our case. Okay, thanks, yes.
Yeah, so that is, well, then in principle, my motivation is the following. So we have since the original works of Baxter's, we have the certain paradigm of the integrability, and unfortunately, with no other way to build. I don't know, at least my opinion, that there's no interest. Non-trivial way to construct the integrable system beyond this integrability. And but Baxter gives us the models, already, which is like this generalization, like a multiparametric homogeneous 6-vertex model, and for the which not studied at all. Since beginning of 70s, nobody studied. Well, at least a few people who some consider this special cases. But I think there are many interesting phenomena may happen there. For example, I mentioned here about the anisotropy parameter for the model. So you see that this is Baxter model with the anisotropy parameter Q, and you see the K is integers and beta squared from 0 to 1. The Q, it's belong to the circle, but not whole circle, but only the certain arc of the model. But you can choose another domain of parameters, and you'll find the absolutely different physics. In particular, you can find the continuous spectrum of conformal dimensions and the theory which is related, describe the, well, like a black hole, the two-dimensional black hole and stuff like this. So many interesting phenomena behind this, and it's mostly unexplored.